Okay, so this is section 4.5, and what we're going to do is we're going to learn how to factor really high-level polynomials. So we know how to factor a lot of different ones so far. Now we're going to factor x to the fourths and x to the fifths and even higher levels. So we have to start with a couple theorems, and the theorems are pretty important. So I'm going to go through the first two kind of slowly. The first one's called the remainder theorem. Now remainder means when you do some division, what is left over after you do the division. So first let's just practice a quick synthetic division just for practice, because we haven't done that this year yet. If I take the polynomial 3x squared plus 7x minus 20, and I divide it by x minus 2, synthetic division looks like this if you remember. You put the 2 on the outside, and then I copy the coefficients only of the polynomial 3x squared. Alright, and then synthetic works like this. You drop the first number down, then you do 2 times 3 is 6, add those together, I get 13. 2 times 13 is 26. Add those together, I get 6. And then what this means is it's not 3, 13, 6. It's actually 3x plus 13, remainder 6. And remember, the way we write remainders is 6 over x minus 2. So that's one way to find a remainder. Now this theorem is kind of a shortcut. What the theorem says is if you divide it by x minus k, or x minus 2 in our case, the remainder is going to be f of k, or f of 2 for us. So f of 2, if you take a look, let's just check it out here, would be 3 times 2 squared is 4, plus 7 times 2, minus 20. And if you crank that through, you get 6 as well. Alright, so now you guys try part B, do the synthetic division, find the remainder, write your answer in this pretty form here, then try the shortcut, find f of negative 1 and make sure it checks out. Alright, now this next one's called the factor theorem. The factor theorem and the remainder theorem go hand in hand. So we're actually doing the exact same thing, but what the factor theorem says is once you crank the remainder through, if you get 0 remainder, then it's actually a factor. And that's what we want. We want to know, is it factor or not? So if I look at this first one, the first one says take this polynomial and divide it by x minus 1. Now, based on the remainder theorem, I'm going to find p, or f, doesn't really matter, p of 1, and now what I'm checking is the answer 0 when I'm done? So these questions are going to be kind of a yes or no. So if I plug in 1, I get 1 minus 3 plus 1, so I get remainder 2. So the question, is it a factor or not? We say no. Okay, let's do the same thing with part B. This time I'm going to find p of negative 3, and if I plug this one's actually kind of kooky, but so I'll grab a calculator probably. 3 to the 4th plus 3 times 3 cubed, 16 times 9, and then it keeps going, minus 27 times 3 plus 63. Now again, this one looks a little crazy, but believe it or not, when you crank all that out, you get 0. So the question, is it a factor or not? The answer is yes. Alright, so this next one is kind of the meat of this whole lesson, the rational zeros theorem. So now what we're going to do is we're going to take some higher level polynomials. So if you look at number 3, for instance, there's no way to factor it by hand. You can't group it, you can't do product and sum, but there must be a way to factor it. So now what we're going to use is the idea of p over q. Now p is the factors of the last number or the constant term. So even if the terms are rearranged a little bit, this negative 2 over here, that's how I'm going to get my p's. And then the q's are the factors of your leading coefficient, so in this case it's a 3. So when I say give me all of the possible factors, now this doesn't mean that every single one of these is going to work, but the possible factors, the only things that will possibly factor into this are the factors of negative 2, so positive negative 1, positive negative 2, over all the factors of q. So for 3, positive negative 1, positive negative 3. So now when I ask what are all the things that could factor nicely, the integers and the rational numbers, they'd be 1 over 1 is 1, 1 over 3 is a third, 2 over 1 is 2, 2 over 3 is 2/3. Now all of these are plus minus, so we don't know which one it is until we do some of the math. Then, once we have all these listed, the possible ones, we're actually going to use a table feature in our calculator. Now, if you're not familiar with the table feature, no biggie, I'll go over that in class. But essentially what's happening is we're trying to find f of each of these factors, right, there's a bunch of them. So if you count them up, there's actually 8 of them because there's 2 of each. F of each of these functions, or factors, and I'm trying to see which one or ones give me 0. So again, the table feature in the calculator is pretty handy. I'll show you that in class. But for now, let's just trust that when I put 1 in, I get 0. Okay? You could actually do the numbers if you want to check that. So then, I get the 1 number from my calculator or from plugging in, and then I go into synthetic division with that first number. So I'm going to use 1. I'm going to have the original polynomial up top, do my synthetic, do this kind of fast, and I get 0 remainder. So if I get 0 remainder, then I know I'm on the right track. So now I know x equals 1 is definitely a factor. Now this thing that's left over is actually 3x squared plus 7x plus 2. And if I take a close look at it, this factors as well. So now I can see 3x plus 1, x plus 2. So now I can see my other two factors, negative a third and negative 2. So if I list them all out, it'd be negative third, negative a 2 from the factoring, and then an extra little 1 at the end from the remainder in the factor theorems. So now I have all of the zeros of this polynomial. Okay, now I want you to try the next one, number 4. I know if you look at it, it actually does group, but I want you to practice with the P over Q's, the synthetic division, and then the factoring at the end. Okay, this next one's pretty tough, so I'm going to do this kind of slowly. We're going to do it in a lot of different steps here. First of all, I want to point out something a little bit different about the directions. It says which one is rational and which one is irrational. So rational, those are numbers that can be written as a ratio, like a half, 5/7, whoops, even just plain old 6 is rational. Irrational means when you do the work and work it out, it does not break down into a nice fraction. So root 3 would be irrational. Root 10 would be irrational. So if you do it in your calculator, it gives you a bunch of decimals that never repeat, and you can't write them as a fraction. So this one means I need to do all of the same math, but then at the end, I need to say this one is rational, this one is irrational. Okay, so let's jump into P over Q. So P over Q, all the factors of P would be 10. So it would be plus minus 1, 2, 5, and 10. And then luckily on this one, all the factors of the Q are just 1. So really I can already see my factors there. Okay, so again, I go into the table feature of my calculator, or I do the rational zeros theorem, and I end up seeing that x equals 2 is one working factor. Now you could probably go in the table or in your calculator and find all the other ones, but I do want to see the work on these. So now what we're going to do is we're going to take that 2 and we're going to do synthetic division with it. Okay, alright, so here's synthetic. Just start working this out. Hopefully we get 0 remainder at the end. Oh, I didn't. Hang on. Back up. 1, 2, 1, 2. There we go. Hang on. There it is, back here. 2. So this should have been a negative 5, negative 10, negative 5. Hang on, my negatives and positives are skewy. Alright, there we go. Negative 10. Whoops. No, my stylus isn't working. There we go. And 0 remainder. Okay, finally. Now this thing that I have here is x cubed plus x squared. Oh, stylus trouble. Alright, minus 5x minus 5. And then this thing groups. I'm kind of running out of room here, but let's just trust the grouping. It would group to x plus 1, x squared minus 5. Okay, so now I can kind of see my answers. I know x equals 2 works. That's the one that I got first. I know x equals negative 1 works from my factoring.
That's mine.
And then, if I do the next step, I get plus minus root 5. Okay, so if I write them all out here, I got my answers. Now I need to answer the rational, irrational part. So 2 and negative 1, those are my rational zeros. And then plus minus 5, that one is my irrational 0. Okay, now just to make something clear, when I do my P over Q, so if I look over here back at my P over Q's, those are only for rational zeros. You see root 5 and all those numbers do not appear on that list. So P over Q only gives me rational zeros. Okay, this last rule, Descartes' rule of signs, it's more of a check at the end of things, but it is good to see, and you should expect it on quizzes and tests. So let's go over it real quick. What it does is it tells me the possible number of positive real zeros and the possible number of negative real zeros. It doesn't tell me what the zeros are. I use synthetic division and all the things we've been talking about to do that. This just tells me how many of each could there be. Okay, so Descartes' rule of signs works like this. If you look at a function, you're going to count the number of sign changes. So take a look at number 6. It goes from a positive 5 to a positive 2. It did not change signs. But then it goes from a positive 2 to a negative 6. So I would say that is one sign change. So if I say, what's the number of possible positive zeros, we're going to say 1. Okay, now if I want to check for negative zeros, I actually find f of negative x. So I plug in a negative x everywhere, and I get 5x to the 4th plus 2x squared plus 6x minus 5. And if I go through and count the sign changes, again, I see only 1. So the number of possible negative zeros is 1 for this one. Okay? Alright, so that one wasn't super exciting because it was just 1 and 1. Now this next one is a little bit more exciting. Okay, let's do the same thing for this one. Alright, let's first count sign changes. So it goes from a positive to a negative, there's 1. Negative back to positive, there's a second one. There's a third one. There's a fourth one. There's a fifth one. So the number of possible positive zeros is 5. Now, if you read the definition up top, it says, or less than even integer. So less than even integer means now I'm going to go down by 2's. So there could be 5 positives, there could be 3 positives, there could be 1 positive. Now you don't go into the negatives because now we're counting things. Okay, now let's do f of negative x. So let's plug in all the negatives. Look what happens. Every single one of these is negative when I plug in negative x. So when I say what's the number of possible negative zeros, we're going to say 0. There are none.